Hi, everybody. Glad to see you again. And let's start our lecture number 3. Okay, so 1 second and just need to start. So let's continue these subtopics on certainty aspect. And more detailed subtopic, nonlinearity and hysteresis. The resolution indicates the smallest detectable increment of the input quantity. Okay, so when we measure, the measurement varies continuously, the sensor output might show discontinuous step, and the value of the corresponding smallest detectable change in the input variable is called the resolution, delta x. Sometimes this parameter is related to the maximum value x that can be processed as a full-scale value, and resulting in the resolution expressed as a delta x minimum over x or delta x maximum over delta x. And this mixed use of definition and maybe sometimes seems confusing. But also, it is easy to see from the unit or the value itself which definition it is. Formally, the accuracy reflects the closeness of the agreement between the actual measurement result and true value of our measurement. So, the accuracy specification should include relevant conditions and other quantities. Many sensors manufacturers specify the sensor performance in the terms of accuracy. And this specification should be viewed with suspicion. Why? Because it may or may not include particular imperfections of our sensor, like nonlinearity, hysteresis, and drift, and may be only valid under strict conditions. So, precision is not the same as the accuracy. Actually, the term precision should not be used in any case to avoid confusion. Most sensors are designed to such that the output is 0 at 0 input. Well, it's logical, right? If the transfer characteristic does not intersect the origin, it means coordinate x, y equals 0, 0. In this case, the system is said to have offset. The offset is expressed in terms of the input or the output quantity. Specifying the input offset is prepared to facilitate a comparison with the value of the measurement. A non-zero offset arises mainly from component tolerance. Offset compensation can be performed in the interface electronics or the signal processing unit. Once adjusted to 0, the offset may nevertheless change due to the temperature variation, due to the changes in the supply voltage, or aging effect. This relatively slow change in the offset is called zero drift. In particular, the temperature-induced drift, or maybe it's called temperature coefficient of the offset, is an important item in the specification list. Sometimes a system is deliberately designed with offset. And many industrial transducers have a current output ranging from 4 to 20 milliamperes. This facilitates the detection of cable fracture or a short circuit, producing a zero output clearly distinguishable from a zero. You know, electrical noise is a collection of spontaneous fluctuations in current and voltage. They are present in any electronic system, arise from thermal motion of the electrons, and also from the quantized nature of electric charge. So electrical noise is also specified in terms of the input quantity to show its effect relative to the value of the measurement. White noise. This is a noise with constant power over a wide frequency range. So white noise is usually expressed in terms of spectral noise power, measured from watt over hertz. Spectral noise voltage, volt over square root from hertz, or spectral noise current, thermal noise is an example, namely white noise. Another important type of noise is 1 over air frequency noise, 1 over noise, RF noise rate. This is a collection of noise phenomena with a spectral noise power that is proportional to frequency, with n between 1 and 2. Quantization noise is the result of quantizing of an analog signal. The rounding off results in a continuous deviation from the original signal. And this error can be considered as a signal with zero mean and a standard deviation determined by the resolution of the AD converter. Do you agree with me? Okay, nice. The response time is associated with the speed of change in the output on a stepwise change of the measurement. So you can see every step in this slide. One step, another is more suitable for step. The specification of the response in the output on a stepwise change needs to be always accompanied with an indication of the input step. For instance, it may be FS, sometimes so often used, it means full scale. And the output range for which the response time is defined. For instance, from 10 to 90%. The possible presence of creep and oscillation may make the specification of the response time meaningless or at least misleading. All specification items only apply within the operating range of the system, which should also be specified correctly. It is given by the measured range, the required supply voltage, the environmental conditions, and possibly other parameters. The frequency characteristics and noise behavior of an accelerometer are very important features. And in this slide, you may see the table is an excerpt from the data sheet of industrial accelerometer. One accelerometer. Many humidity sensors have nonlinear behavior. And namely, this table is an example of the specification of a typical industrial humidity sensor. RH stands for relatively humidity. So you may see operation gain rate. Despite the specification limitations of sensors, a sensing system can be configured in a way that the effect of some of these limitations is eliminated or at least reduced. We consider various possibilities of error reducing this design a bit later. Okay, so any sensor system has imperfections. You already know. Introducing measurement error. And these errors either originate from the system itself, for instance, system noise, quantization, and drift, or are due to the environmental influences such as thermal, electromagnetic, and mechanical interface. Sensor manufacturers try to minimize such intrinsic errors through proper design of the sensor layout and encapsulation. The remaining imperfections should be given in the data sheet of the sensor. And the user, for instance, the mechatronic designer, should minimize additional errors that could arise from improper mounting and faulty electronic interfacing. In this part of our lecture, we present some general concepts to minimize or to reduce the effect of the intrinsic errors when applying sensors. You know, usually sensor is designed to be sensitive to just one specific quantity, thereby minimizing the sensitivity to all other quantities, despite the unavoidable presence of many physical effects. And the result is a sensor that is sensitive not only to the quantity to be measured, but also in a greater or lesser degree to other quantities. This is called the cross-sensitivity of the device. Temperature is feared most of all, illustrated by the saying that every sensor is temperature sensor. So, besides cross-sensitivity, sensors may suffer from many other imperfections. They influence the transfer of the measurement signal and give rise to unwanted output signals. And this slide shows a simplified model of a sensor system with an indication of several error sources. And you can see here as a symbol XD, as F, E, epsilon, D, and F. So in this figure, on the left corner, XM is a measurement signal, and the opposite side, on the right, Y naught, the output signal. Additive error signals are modeled as additional input signals. It's both XD and XF represent deterministic SD and XF stochastic error signal respectively. So deterministic and stochastic signal. They model all kinds of interference from the environment and the equivalent error signals due to system offset and noise. Okay? The error inputs epsilon D and epsilon S represent multiplicative error. This signals effect of sensitivity of the sensor. For this simplified model, the output signal of a sensor, here you can see, can be written according to this equation. In this equation, S is the nominal sensitivity. This model will be used to evaluate various error reduction methods. And some of these methods will reduce mainly additive sensors, and others minimize multiplicative sensors. Improvement of sensor performance can be obtained through use of a sophisticated design or simply through some additional signal processing. In today's lecture, we discuss 5 basic error reduction methods: compensation, feedback, filtering, modulation, and correction. The methods apply not only to sensors, but also to other signal handling systems, as amplifiers and signal transmission systems. Compensation is a simple and effective method to minimize additive errors due to interference signals. The basic idea is as illustrated in this figure, namely in figure A, on the left part of this slide. A, the output of the sensor of Y node, and you can see usually at the right side. The Y node contains unwanted signal components. For instance, due to the interference X or offset. From this output, a compensation voltage Y sub C is subtracted so that you can see the minus. The condition for full compensation is equal YC equal S times XI, making the Y node S times XF, independent of X, as you can see, X absent. Yeah. So for correct compensation, the interference signal S, as well as the sensor transfer S1, sensor transfer S, should be known. One way to accomplish compensation is by adjustable compensation signal. What it means? It means a zero input Y1 is manually adjusted to a value for which the output is zero. A more elegant way to compensate is to apply a second sensor, as illustrated in figure B. The measurement signal SM, XM, yes, you can see it here in this one, is supplied simultaneously to both sensors, upper and S1 and S2 up and down. So it's like two strain gauges, one loaded on compressive stress and other on tensile stress. Okay, so and minus sign represents the opposite sensitivity of a sensor, and the two output signals are subtracted by a proper electronic sequence. Because of the anti-symmetric structure with respect to the measurement signal only, many interference signals appear as common output signals, and thus are eliminated by taking the difference of the two outputs. The effectiveness of the method depends on the degree of symmetry of the double sensor or differential sensor structure. From this figure, it is follows our equation, where here S in both sides transformed in figure B, S1 and S2 are the sensitives for the measurement signal and the interference signal respectively. K may be used only 1 and 2. So the output signal of the sensor system equals, as you can see in row 3 in this slide, and becomes like expression for Y node. Right column, and the expression. Analogous to the definition of the rejection ratio for differential amplifiers, we can define a quality measure for the imbalance of the differential sensor. This you may see the second equation in our right column. A parameter characterizing the system's ability to distinguish between measurement and interfering signal. Okay, let's go. The method is illustrated with a two active element with stone measurement bridge, as you can see on this slide. In this curve bridge mode, R1 and R2 are fixed resistance, and R3 and R4 are resistors sample. Their resistance values change with a particular physical quantity as well as an interfering signal, according to the second equation. So here, you may find that S is the sensitivity of sensor to the measurer, for instance, deformation. Okay, and SI in this case, in both cases, is the sensitivity to the interference signal, like, for instance, temperature. So we should notice that in this system, the sensor resistance is just R at a particular initial value of the measurer and at zero interference. Okay? Okay. Assuming both sensor parts experience the same measurement signal and have equal but opposite sensitivities to the measurer, the bridge output voltage satisfies approximately the equation right here. So if both sensor parts have equal sensitivity to interference by symmetric sensor design, and both sensor parts experience the interference equally, the error term in our last equation on the bottom should be equal to 0. And the interference is completely eliminated. That's nice. So this last equation is useful to make a quick assessment of the error due to the asymmetry or relative to the measurement signal. Let's look one example. So if we have resistors R1 and R2 in our figure, and these resistors are strain gauges with our strain sensitivity, like K or gauge factor, and alpha measured in Kelvin. So the measurement signal is the relative deformation or strain, our delta L over L, and the interference signal is a change in temperature theta. So the transfer of this bridge is here on the bottom, you can see. And here we can find that delta theta is the temperature difference between the two sensor parts. And delta alpha is the difference in temperature sensitivity. So in a proper design, both sensor parts should have the equal temperature and equal temperature sensitivity over the whole operating range. Another subtopic, feedback method. Feedback is an error reduction method originating from the early amplifiers with vacuum tube. Their unstable operation was a real problem until the application of feedback, which reduces in particular multiplicative error. And this figure A, on the left part of this slide, shows the general idea. What it means? Suppose we have a sensor that has a nominal transfer F, but due to the multiplicative interference, it has changed to the F as times 1 plus X. And the feedback is accomplished by an actuator with an inverse transduction effect and transfer case. Okay? And from classical control theory, the error reduction factor can easily be found. Then transfer of the total system, SF, you may see from this first equation, is given by this equation. A feedback system we have here as a basic configuration. On the figure B, we have with configuration with additive interference signal. a relative change as DSF in the terms of transfer S causes a relative change ds in S according to our second equation. Yes. Okay. So in an appropriate feedback system design, it's maybe only in case when Ks much higher than 1. And so in this case, the relative error in the forward path is reduced by a factor equal to the loop gain. Loop gain is the S times K of our system. And the penalty for this improvement is the reduction of the overall sensitivity with the same factor. So, so often feedback also reduces additive interference signal in a degree that depends on the point of injection in the system. Two cases are discussed in this figure B. The output due to the interfering signal xi1 and xy2 equals on the equation here on the bottom. Obviously, signals entering as the input of the system are reduced by feedback as much as the measurement signal. So the SNR is not better. And interfering signals injected at the output of the sensing system are reduced by factor S. And that reduces more than the measurement signal. So our SNR is increased by the same amount. Do you agree? Okay. And at the same time, feedback reduces error in the forward signal path. How it means? The transfer is mainly determined by the namely feedback path from a main and back. And nonlinearity in the forward path from xm to y0. For instance, we may say due to nonlinear sensor characteristics is also reduced. And provided a linear transfer of our feedback element. Prerequisites for an effective error reduction are as follows. It's only two. First is a high forward path transfer, and second, stable feedback path transfer. Okay, let's go. The application of this method to sensor requires a feedback element with a transfer that is the inverse of the sensor transfer. Imperfections of the sensor are reduced. However, the demands on the actuator are still high. This method is illustrated with an example of a capacitive accelerometer system in which two error reduction methods are combined. Compensation by balanced sensor construction and feedback by an inverse transducer, as you can see in this slide. Okay? A displacement of the seismic mass M results in a capacitance difference delta C. So seismic mass and that transformed to the capacitance delta C. And this value is converted to a voltage which is compared with the reference value. And here this value in our case equals 0. The amplifier voltage difference is applied to an electromagnetic actuator, and you can see here in the wire, that drives the mass back toward to its initial position. And when the properly designed, the system reaches a state of equilibrium in which the applied inertial force is compensated by the electromagnetic force from actuator. And the current required to keep equilibrium is a measure of the applied force or acceleration. A more detailed model of this system, for instance, for stability analysis, is depicted, namely in this figure. All transduction steps are visualized in separate blocks. Obviously, the feedback is performed in the mechanical domain by counteracting the inertial force Fi with the electromagnetic force Fa, often actuated. Okay? So the transfer function of the whole system can easily be derived from this model and is given in left, and we can see this first equation. Here, HA is a transfer from applied acceleration to inertial force Fi. HS is a transfer of the mechanical spring. It means from force to displacement delta F. Okay? The transfer of the electrical system, like capacity sensor, electronic interface, and amplifier together, is HE. So finally, HA is a transfer of actuator. If we have conditions HA, HI, and HE, both multiplicated, should be much higher than 1. In this case, the transfer function of the total sensor system becomes as this equation on the right side. Very simple, right? Very nice. So indeed, this is independent of the spring stiffness, the sensor transfer, the interface, and the gain of the amplifier according to the feedback principle. In equilibrium, the mass is at its center position, and hence no particular demand have to be made on this spring and sensor. So no particular spring, sensor, and certainly interface sequence. The only requirement is a small zero error. So actually, the requirements with respect to the sensor quality have been transferred to those of the actuator. The system transfer depends only on the seismic mass, M on the left side of this scheme, and the actuator transfer, HA. Okay? And our feedback may also improve the dynamic performance of the sensor. Assume the sensor in this figure the same, identical, right? And is a mass spring system that described by the general second order or complex transfer characteristic. We describe this by this first equation. Here we have as ZF as a damping and omega F as the natural or undamped frequency of the resonance or resonance frequency. Substitution in our equation, provision slide, results in the transfer of the system with feedback, as we can see in our next a bit more complicated equation. By the way, you should not memorize all of this equation. You should only understand how we can do. Okay, so let's go. So in this case, the system has become faster by feedback. The principle is also applicable for other measurements. For instance, pressure. Many pressure sensors are based on a flexible membrane that deforms when a pressure difference is applied. And usually, this deformation is measured by some displacement sensor providing the output signal. The effect of the strong nonlinear response of the membrane can be eliminated by feedback, as you can see here on this. And using only a linear actuator in the feedback part. By the way, there are various sensors on the market that are based on the feedback principle. Next subtopic, filter. Error signals can be reduced or avoided by filtering, to be performed either in the domain of the interfering signal prior to transduction or in the electrical domain after transduction. The unwanted signal may be kept outside the sensor system by several filtering techniques, depending on the type of signal. Sometimes the technique is referred to as shielding. We briefly review some causes and associated reductions. And first of all, this is electric injection of spurious signal through a capacitive connection between the error voltage source and the system input, to be avoided by a grounded shield around the sensor structure and the input lead. The capacitively induced current flows directly to ground and does not reach the input of the sensor. The second, magnetically induced signal by a time-varying magnetic flux through the loop, and it made up by the input signal. In this case, cannot only be reduced by a shield made up of a material with a high magnetic permeability, but also by minimizing the area of the loop. And this is leads close to each other, or as we said, twisted. Fourth is the changes in environmental temperature, or thermal shielding and encapsulation with high thermal resistance, or a temperature-controlled housing, which reduce thermal effect. Fourth, unwanted optical input from lamps, the sun, and so on. All of that can be stopped by optical filters. You know, many filter types are available today on the market. Measurement and interferences should have a substantial difference in wavelength. And finally, mechanical disturbances, like shocks and vibrations, which are reduced by a proper mechanical construction with elastic mounting and performing suitable damping of the vibration. Another subtopics, filtering after transduction. In case the interfering signals are of the same type in the same signal domain as the measurement itself, our error reduction is accomplished with the filter based on differences in particular properties of the signal. For electrical signals, the distinguishing property is the frequency spectrum. Electrical interfering signals with a frequency spectrum different from that of the measurer and can easily be filtered by electronic filter. If they have overlapping frequency spectra, this is not only partially possible. In this case, solution to this problem is to modulate, if it's possible, certainly, modulate the measurement signal prior to transduction to create a sufficiently large frequency difference, which enabling effective filtering in the electrical domain. Another subtopic is modulation. Modulation of the measurement signal is a very effective way to reduce the effect of offset errors and noise. We shortly review the basics of amplitude modulation and demodulation and show that this combination behaves as a narrow band pass filter process. So, modulation is a particular type of signal conversion that makes use of an auxiliary signal, the carrier. One of the parameters of this carrier signal is varied analogously in the input or measurement signal. And the result is a shift of the complete signal frequency band to a position around the carrier frequency. And due to this property, modulation is also referred to as frequency conversion. And I should stress it to your attention that a very important advantage of modulated signal is their better noise and interference immunity. In measurement systems, modulation offers the possibility of bypassing offset and drift from the amplifier. Amplitude modulation is a powerful technique in instrumentation to suppress interference signals. Therefore, we confine to amplitude modulation only. Okay? A general expression for amplitude modulation, AM, signal with a sinusoidal carrier with C modulated by an input signal V from T is followed as this equation. Here we have dub omega C is the frequency of a carrier. And as a second variation, we have a K is a scale factor, which is determined by the modulator. Suppose the input signal is a pure sine wave. In this case, the modulated signal is as follows expression for these numbers. This expression shows that this modulated signal has three frequency components. One with the carrier frequency, omega C, right? One with a frequency equal to the sum of the carrier frequency and the input frequency. And this we call the omega C plus omega I. And one with the difference between these two frequencies. And we can see as this one, omega C minus omega I. Okay, so we can transform our second equation in this large equation, right? Okay. And the upper figure here on this slide shows us an example of such an amplitude modulating signal. The input signal is still recognized in the envelope of the modulated signal, although its frequency component is not present. But once the carrier is modulated by an arbitrary input signal, each of the frequency components in its spectrum, as you can see from middle figure in B, produces two new components with the sum and the difference frequency. And hence, the whole frequency on the figure C has it's a full, we have four whole frequency band, which is shifted to a region around the carrier frequency in both sides. And these bands of either side of the carrier are called the side bands of the modulated signal, as left side band and right side band. The AM amplitude modulated signal does not contain low frequency components anymore. Therefore, it can be amplified without being disturbed by offset and drift, which allowed, as you can see now, maybe it's a low frequency signal. If such frequencies appear anyway in the amplified modulated signal, they can easily be removed by a high pass filter. There are many ways to modulate the amplitude of a carrier signal. We discussed only three methods: the multiplying modulator, the switch modulator, and the bridge modulator. Multiplication of two sinusoidal signals, VC and VI, carrier and input, result in an output signal, if you can see on this equation. Here in this equation, the capital letter is the scale factor of our multiplier. This signal contains only the two side bands component and no carrier. And in this case, it is called an AM signal with suppressed carrier. For arbitrary input signal, the spectrum of AM, amplitude modulation, signal consists of two identical side bands without carrier. And namely, upper figure A, shows an example of such MA and AM signal. We should notice that the envelope is not identical to the original signal shape anymore. Furthermore, the AM signal shows a phase shift in the zero crossing of the original input signal, as you can see on the bottom figure B. In the switch modulator, the measurement signal is periodically switched on and off, and a process that can be described by multiplying the input signal, which is switch signal F from T, being 1, when the switch is on, and certainly it's equal 0 when it is on, right? So to show that this product is indeed a modulated signal with sideband, we expand S from T into its Fourier series, as you can see in this equation on the bottom. Generates very simple. And here we have omega proportional to pi over T. T capital here is the period of a switching signal. For our sinusoidal input signal with frequency omega and each of the components of S from T. Right? Okay. This modulation method produces a large number of sideband pairs positioned around odd multipliers of the carrier frequency. Omega, 3 omega, 5 omega, and so on. As you can see here. The low frequency component originates from the multiplication by means of S from T. And here we have only 1 over T. And this low frequency component and all components with frequency 3 omega C and higher can be removed by our filter. And the resulting signal is just an AM signal with suppressed carrier. Advantages of the switch modulator are its simplicity and accuracy. It means the sideband amplitude is determined only by the quality of the switch. A similar modulator can be achieved by periodically changing the polarity of the input signal. And this is equivalent to the multiplication by a switch signal with 0 mean value. In that case, there is no low frequency band, as you can see in this picture. The absence of DC and low frequency components considerably facilitates the amplification of modulated signal. How does this mean? It means basically offset, drift, and low frequency noise. All of them can be kept far from the new signal frequency band. And when very low voltages, it must be measured. It is recommended to modulate the prior to any other analog signal processing that might introduce DC error. The principle of the bridge modulator is illustrated with the resistance measurement bridge or Wheatstone bridge, as you can see in this figure. The Wheatstone bridge is connected to an AC signal source we have defined here as YI. This AC signal, usually a sine or a square wave, acts as a carrier. And in this example, we consider a bridge with only one resistor that is sensitive to the measure. That is sensitive to our measure, right? Assuming equal values of 3 other resistors, the signal V3 is just half the carrier, whereas the signal V4 is an AM signal, and it is equal half the carrier modulated by R, right? And the bridge output of V0, you can see here, between this and this, is the difference between these two signals. So it is an AM signal with suppressed carrier, right? Okay. This output can be amplified by a differential amplifier with high gain. It means its low frequency properties are irrelevant. The only requirements are a sufficiently high bandwidth and a high common mode rejection ratio for the carrier frequency to accurately amplify the difference VA and VB. Modulation techniques also apply to many non-electric signals, and optical signals can be modulated using a LED or laser diode. If our source itself cannot be modulated, optical modulation can be performed by, for instance, a chopping wheel, as is applied in many pyroelectric measurement systems. And also, some magnetic sensors employ the modulation principle too. The reverse process of modulation, called demodulation. Sometimes it's called detection. Looking at the AM signal with carrier, for instance, in this figure, we observe the similarity between the envelope of the amplitude and the original signal shape. An obvious demodulation method would therefore be envelope detection or peak detection. And this becomes that the envelope detectors operate only for AM signal with carrier. In an AM signal without carrier, the envelope is not a copy of the input anymore. Moreover, additional information is required with respect to the phase of the input for full recovery of the original waveform. An excellent method to solve this problem, and which has a number of additional advantages, is synchronous detection. Synchronous detection consists of multiplying the AM signal by a signal which having the same frequency as the carrier. If the carrier signal is available, as in the case in most measurement systems, this synchronous signal can be carried itself. Assume a modulated sinusoidal input signal with suppressed carrier, as you can see in our first equation expressed as Vm. This signal Vm is multiplied by a synchronous signal with a frequency equal to that of the original carrier and the phase angle phi. You can see here at the bottom. The results, as we can see here in next equation, and with a low pass filter, the components around 2 omega c in this fourth part are removed, leaving the original component with only frequency omega. This component has a maximum value for phi equals 0. And that is when the synchronous signal has the same phase as the carrier. Suppose phi equals half phi. The demodulated signal in this case is 0, and it has the opposite signal for phi equals phi. And this phase sensitivity is an essential property of synchronous detection. And this figure reviews the whole measurement process in terms of frequency spectrum. The starting point is the low frequency narrow band measurement signal A. And this signal is modulated and subsequently amplified. The spectrum of the resulting signal is detected on the figure B of the list. showing that the AM spectrum of the measurement signal and some additional error signal introduced by the amplifier. What we have? We have offset in this part on the beginning. It's a DC. Drift, it's equal only 1 over F noise, LF, and wideband terminal noise. And the bottom figure shows the spectrum of the demodulated signal. By multiplication with the synchronous signal, all frequency components are converted to a new position. The spectrum of the amplified measurement signal falls back to its original position. And our LF filter error signal converted to a higher frequency range. Simply shifted to right side, right? A low-pass filter removes all components with frequencies higher than that of the original band. And an important advantage of this detection method is the elimination of all error components that are not in the small band of the modulated measurement signal. If the measurement signal has a narrow band or slowly fluctuating measurement quantity, we have a low cutoff frequency of the filter that can be chosen. Hence, most of the error signals are removed, and a remarkable improvement of the SN ratio is achieved even with a simple first-order low-pass filter. The low-pass filter with bandwidth B acting on the demodulated signal is equivalent to a band-pass filter acting on the modulated signal for around the curve. This means that the effective bandwidth is too big. The sensitivity of a band-pass filter is expressed with the quality factor Q. This factor defined as a ratio between its central frequency F and, minus 3 decibel bandwidth for B. So, the synchronous detector can be conceived as a band-pass filter with quality factor equal F over B. If, for example, the measurement signal has a bandwidth of half hertz, then the cutoff frequency of the low-pass filter is also set to half hertz, right? Suppose the carrier frequency is 4 kHz, then the effective quality factor of the synchronous detector is 4000. An active band-pass filter can achieve 2 factors of about 100 at most. So, synchronous detection offers a much higher selectivity compared to active filters. And erroneous and correction sensor signal can be corrected if knowledge about the causes of error or the value of error is available. Two different strategies can be distinguished here. It's first, static correction, and second, dynamic correction. If the first class of strategy, correction, is performed while leaving the sensor unaltered. In this figure shows the general configuration for two approaches. In the model-based approach, the sensor signal is corrected based on prior knowledge about the origin of the error. For instance, nonlinearity or a calibration curve, which stored in a lookup table. If the errors are unknown, in case of interference, the error signal could be measured separately by additional sensors. The output of this sensor is used to correct the original sensor signal. And the method is straightforward, but requires additional sensors, at least one for each type of interference. So in any case, we have advantage and disadvantage, right? Dynamic correction involves a particular sensor design. Basically, the method involves a series of measurements of the same quantity in such a way as to eliminate the errors by post-processing. And this can be done in various ways, according to the type of quantity and error. First is multiple input signal measurements, eliminated scale and offset error. Second, cycling, interchanging of components, or dynamic patching. And third, cycling, changing the sensitivity direction of our sensor, or flipping. The first method of multiple input measurements is illustrated in this figure in the top. Additive sensors are represented by the signal X. Multiplicative error due to the interfering signal X are represented by relative error epsilon. Alternatively, the input of the system is connected to the measurer, yielding out our output Y0 to ground, or giving output Y, and to reference, resulting in our output. The three system output are as follows. As you can see, is this three left equation. From this equation, the measurement can be calculated according to this expression. Offset and scale errors are completely eliminated if the errors do not change during the sequence of the three measurements. The method requires a reference of the measurement type as well as possibility to completely isolate the input from the measurement to find the offset error contribution. For most electrical quantities, like voltage, capacitance, and resistance, this is quite an easy task. This is not the case for many other physical quantities, because repetitively short sequentially circuiting the input of a magnetic field sensor or a force sensor, for instance, without removing the measurement itself, requires complicated and therefore impractical shielding techniques. All sensor systems suffer from offset and drift, which hampers the measurement of small, slowly varying signals. Modulation, as discussed earlier, is a very effective way to eliminate offset. However, modulation of the input signal is not always possible. An alternative way to reduce offset is flipping the directivity of the sensor without changing the sign and value of the offset. So clearly, the method can only be applied for sensors that are sensitive to the direction of the input quantity, which should be a vector, right? So flipping is performed either by changing the carrier signal in modulation sensor or by rotation of the sensor itself. An example of a modulating sensor is the Hall sensor for the measurement of magnetic field strength. This is a modulating type sensor because the output is proportional to both the input signal and auxiliary signal, in this case, a DC bias current. Assuming the offset being independent of the bias, the offset reduction follows from our this second equation. Here, XC in the bottom we see is the carrier signal, which is flipped between two sensitive measurements. You know, obviously, the difference between the two outputs is proportional to the input signal and offset independent. When the sensor is not of the modulating type, the same effect is obtained by just rotating the sensor. Since this mechanical flipping requires some moving mechanism, the method is restricted to low frequency application. But all error reduction methods discussed in our lecture are illustrated schematically in this slide. In this scheme, the basic signal flows is shown in dark color. The performance of a non-compensated sensor can be improved by adding error-reducing systems. For instance, filters, modulators, and correction circuitry. And it has a custom. When designing a sensor system, other techniques are worth consideration. For instance, the inclusion of a compensating sensor in a balanced configuration. And here, this is a white part. During the design process of a particular sensing system, it is recommended to consider all these possibilities in connection to the possible occurrence of error. Another part of our lecture is the resistive sensor. The sensors presented in today's lecture are all based on resistive effect. Namely, they behave as an electrical resistor whose resistance is affected by a particular physical quantity. Quantities that can be measured using a resistive effect are temperature, it may be thermistor and metal thermometer, light by light-dependent resistor, deformation is a resistor, and magnetic field strength magnetoresistor. By a special construction or material choice, resistors can be made useful for sensing various quantities. For instance, force, torque, pressure, distance, angle, velocity, and acceleration. After having defined resistance and resistivity, we discussed successively potentiometric sensors, strain gauge, piezoresistive, and magnetoresistive sensors. Moreover, some thermal and optical sensors based on resistive effects are reviewed. The last section in our lecture presents a number of applications of sensitive sensors, including the interface. Another subtopics in this lecture, resistivity and resistance. The electrical conductivity sigma, the inverse of electrical resistivity rho, is defined as the ratio between current density and the electric field strength. I show this on the next slide. So, conductivity is a pure material property. It does not depend on shape or size of the device, like skin effect and thin layer effect that are disregarded here. So, in our lecture, all materials are assumed to be homogeneous. The resistance between the endpoints of a part with length 1 and constant cross-section equals according to this classical equation. R proportional to rho times L over A, right? This, the parameter L is used to create distance sensor and angular displacement sensor. These sensors are called potentiometric sensors. Strain gauges are based on changes over 1 over A applied in force and pressure sensor. While the parameter rho is the property of the interest in piezoresistive, magnetoresistive, thermoresistive, and optoresistive sensors. So, and this table presents the overview of the various resistive sensors which discussed in our lecture. Another subtopics today's lecture, potentiometric sensor. Potentiometric displacement sensor can be delivered into linear and angular type, according to their purpose and associated construction. A potentiometric sensor usually consists of a linear or toroidal body, which is either wire-bound or covered with a conductive film. a slider or wiper can move along this conductive body, acting as a movable electric contact. The connection between the slider and the object of which the displacement should be measured is performed by a rotating shaft. And you can see here on the figure A. Angular potentiometer, a moving rod, an externally accessible slider or sledge type, or a flexible cable that is the cap stretch during the operation. So this figure shows schematic view of some of these constructions. In all cases, the resistance wire or field and the wiper contact should be properly sealed from the environment to minimize mechanical damage and corrosion. This is an important issue when applied in mechatronic systems that operate in harsh environments. Robust potentiometers have a stainless steel shaft or rod and the housing of, for instance, anodized aluminum. The moving parts of the potentiometer are provided with bearings to minimize the mechanical force needed to initiate movement of the slider and minimizing wear. Potentiometric sensors are available in a wide variety of ranges. Linear types vary in length from several millimeters up to few meters. Angular types have ranged from about 5/2 pi radian up to multiply 2 in power 10 of 2 pi, or multi-tone potentiometer, achieved by built-in gears or a spindle construction. The specification of potentiometric sensors is standardized by the Instrument Society, for example, in America. We list here the major items in a short formulation. VR stands for voltage ratio, that is, the ratio between the wiper voltage and the full voltage across the resistor. And here you might see in this case. A manufacturer should mention all the specifications in the data sheet of the device. And this table lists the main specifications for various types of potentiometers. Besides the specification listed in this table, many other parameters should be considered when using a potentiometer as displacement sensor, in particular in mechatronics applications. Some of them are listed below. It's a maximum allowable force or torque from the wiper, minimum force or torque to move the wiper, maximum rotational wiper speed, usually about 1000 RPM, maximum voltage across the resistor, typically 10 volts, and maximum current through the wiper contact, typically around 10 milliamperes. Potentiometric displacement sensor can electrically be connected in two different ways. The potentiometric wiring and the rheostat wiring. We have the change by this wire. In rheostat mode, we can click here, the device acts just as a variable resistor, two terminals. The potentiometer mode is suitable for voltage division, two-port configuration. The VR over potentiometer equals RT over R, which for an ideal potentiometer is equal X over S. L here the electrical stroke, and X is the distance between the start point and the wiper point. So we can measure and have this VP diagram. Nonlinearity and resolution are main causes of a deviation from the ideal transfer. A linear relationship between position and wiper voltage requires a wire or field with homogeneous resistivity over the whole range. The intrinsic nonlinearity can be as good as 0.01%. in 100 times less than 1%, as you can see from this table. Improved interfacing may introduce additional non-linearity. The position resolution of a wire wound potentiometer is set by the number of tunes we have at the end. If we have the R as the total resistance, R capital, total resistance of a single tune amount, we can find as delta R, it's R over M, the quantities of tunes, right? As the wiper steps from one tune to the next, the VR changes left-wise with an amount of 1 over N. When the wiper moves continuously, one after another. Okay? Hence, our resolution equals delta R over R is simply 1 over N. At wiper position on top of tune I, VR equals pi over N, right? Very simple. On top of the next tone, it increases to I plus 1 over N, as you can see here on the next tone. Actually, the wiper might short circuit one tune when positioned just between two windings, and you can between two windings, as you can see here on figure B. In those particular positions, the total resistance drops down to N minus 1 times delta R. And hence, our VR is proportional I over N minus 1, which is slightly more than I over N, right? The resolution can be increased without change of other dimension by reducing the wire thickness. However, this degrades the reliability because a thinner wire is less wear resistant. The resolution of a film potentiometer is limited by the size of the carbon or silver grains that are impregnated in the plastic layer to turn it into conductor. The grain size is about 0.01 micrometer, and the resolution is about 0.1 micrometer as well. The interfacing of a potentiometric sensor is essentially simple, as you can see from this figure. To measure the position of the wiper, the sensor is connected to a voltage source VI with a source resistance RF. The output voltage on the wiper we have V0 and is measured by an instrument with input resistance by RI. And ideally, the voltage transfer V0 over VI equals VR. Due to the presence of a source resistance and the load resistance, the transfer might differ from VR. And we will calculate the error introduced by both these effects. Just assume if we have Ri equals 0. In this case, R0 becomes infinity. And under this condition, the output voltage of the sensor satisfies equation for the linear potentiometer or equation for angular potentiometer. Here we have L. L is the total electrical length, and in next equation we have an alpha. Alpha is the maximum electrical energy. The sensitivity of a linear sensor, if we can see in this equation, and apparently is independent of the resistance R and proportional to the source voltage. The sensitivity can be increased by increasing the source voltage. Obviously, the maximally permissible power should be kept in mind. And when ambient temperature increases, the maximum allowable dissipation drops. It is wise to carefully check the data sheet on this aspect. And instability of voltage results in an output change that is indiscernible to displacement. And that effect is the maximal for in case if X equals L. In this case, a stability criterion for voltage is inequivalent. It may be only when delta X is the smallest detectable displacement. Otherwise, stated the stability of source voltage should be better than the resolution of the potentiometer. A non-zero value of the source resistance introduces a scale error. In our case, if we have R non-zero value, R should become the infinity, and the sensor transfer is, and we can see in this case, this equation, and we can find voltage. Hence, the sensitivity is reduced by an amount of Ri to R with respect to the situation with ideal voltage source. Ideal voltage in case when Ri equals 0. A load resistance, in our case is R, results in additional nonlinearity error. And now assuming Ri equals 0. So the voltage transfer is described by this expression, R over Ri, much time less than 1, right? So the endpoint linearity error in this case, the deviation from the maximum, from the ideal transfer X over L amount, and we can see NL, nonlinearity. The maximum error is this case minus 4 over 27 R times over Ri. If we have XL in case 2 over 6. And this error adds up to the intrinsic nonlinearity error of our sensor, which is due to unevenly binding or inhomogeneity of wire or film material. The relative nonlinearity, if you can see the last equation, from which follows a maximum relative deviation in case of minus 1 over 4 R over Ri, occurring at the position when X over L is a ordered file. Or sometimes we call it midway between the endpoints, right? So both errors are proportional to the resistance ratio R over Ri. And this figure shows the absolute and relative nonlinearity error for the case 1%. In this case, absolute nonlinearity only, in this case in the right, only 15%, only over 15%. So if, for example, the absolute nonlinearity due to the loading should be less than 0.05 over the full range of the potentiometer, then the maximum value for the load resistance should be 300 times that of potentiometer, right? Additional nonlinearity due to possible low input resistance of the measurement instrument can be circumvented by inserting a voltage buffer between the bypass and the measurement instrument. We can see here from this slide. Such a buffering alleviates the requirement on the input resistance of the readout signal. And the influence of source voltage changes and can be reduced by applying a ratio method as illustrated in this slide. The transfer of analog to digital converter, ADC, analog to digital, is here we get, here we know it's equal to Gn times Vn. Gn is a binary coded fraction. It might be between 0 and 1. Since the reference voltage of ADC equals the voltage across the potentiometer, It follows as Gm equals X over X, which in the ideal case does not depend from voltage. So the ADC output can be directly processed by computer. That's very popular today. Interfacing a potentiometer is embedded systems and can be performed without external components. This is illustrated in this slide. Here we have a potentiometer which is directly interfaced to Arduino board. In this case, the microcontroller's supply voltage is used as source for the sensor. When no other or heavy loads are attached to the same source, and in this is a viable solution. In the default configuration, the ADC of the port has the supply voltage as a reference. And the input impedance is high enough compared to the sensor resistance to be neglected. And in this case, the angle of the potentiometer will be linearly mapped to the from 0 to 5 volt input range. Using the conventional implementation of the ADC function in our Arduino, you may say like integer input value or analog signal, the angle of rotation from 0 to 270 degrees is mapped to a value between 0 and 1024. 2 in power 10, not more, right? Nice. Next lecture we will be continuing study resistive sensors. And now I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye. All the best. See you next time.